Hello everyone, welcome to the fifth video of week 2. In this video we will explain a second general principle to construct estimators for parameters, the so-called method of maximum likelihood. To get a feeling for this method, let's start with a very simple example. Suppose we have two dice, one that has 5 blue sides and 1 orange side, and a second one that has 5 orange sides and 1 blue side. Someone chooses one of the two dice and conducts the following experiment. Throw the die until the first time orange ends on top. We do not know which die has been chosen, but the person reports that it took 7 throws. The experiment is repeated again with the same die, which takes 4 throws, and again, which takes 10 throws. Now, given the results of the experiments, can you guess which die has been used? Now, you may pause the video for a moment to give this some thought. You probably chose die number 1. Well, you are not the only one. Most people will choose die 1, and if you ask them why, then they will usually answer something like, well, with so much blue ending on top, it's more likely that die number 1 has been used. Completely right. But what you have not realized is that this example also illustrates the method of maximum likelihood in a nutshell. One chooses the die for which the observations 7, 4, and 10 are most likely to occur. Now, when facing a statistical problem, we do not have to choose between two dice, but between different possible values for a parameter. But the principle remains the same. We choose the value of the parameter for which the observations are most likely to occur. For the dice example, the probability of having 7, 4, and 10 for die 1 is equal to the product of the probabilities of having orange on top for the first time in throw 7 times the same type of probability for having the first time orange in throw 4 times the probability having it in throw 10. This results in a very small number. However, the same probability for die 2 is even much smaller. In fact, the probability of having observations 7, 4, and 10 is for die 1 5 to the power 15 times larger than for die 2. So indeed, the available data are much more likely to occur for die number 1. Let us look at a more complex problem. Everyone who is riding a bicycle and tries to lock it with a wheel lock that is fixed on the bicycle may run into the following problem. You park your bicycle, and when sliding the ring lock to lock the bicycle, you occasionally hit one of the spokes. Now, what is the probability that this can happen? Let us try to estimate this by means of an experiment. Suppose someone conducts the following experiment 3 times. That is, count the number of occasions it takes until you first hit a spoke. In the first experiment, it takes 64 occasions. In the second experiment, it takes only 3 occasions. And in the third experiment, it takes 12 occasions. Now, how do we model our data set? Well, it seems reasonable to assume that hitting a spoke or not at different occasions is independent of each other, and that the probability of hitting a spoke is the same on every occasion. In this way, observation 64 can be modeled as the realization of a geometric random variable with parameter p, where p represents the probability of hitting a spoke. In the same way, our dataset with observations 64, 3, and 12 can be modeled as a realization of independent random variables x1, x2, and x3 with the same geometric distribution with parameter p. Now, using independence, the probability that these observations occur is then given by the product of the following probabilities. Putting together terms with p and terms with 1 minus p leads to p to the power 3 times 1 minus p to the power 76. This expression, which represents the probability of the data, is called the likelihood and is denoted by the letter capital L. Now the question remains, for which value of p between 0 and 1 does the likelihood attain its largest value? Well, this is where statistics meets basic calculus. Differentiating this expression with respect to p and setting the derivative equal to 0 would give us the answer. But before doing so, we make things a bit easier. Since we only want to know at which p the likelihood attains its maximum, and not what the value of the likelihood is, we might as well maximize the logarithm of the likelihood. Because the log function is a monotone increasing function, L and the log of L attain their maximum at the same value for p. Now the motivation to take logarithms is that it changes a product into a sum, and sums are easier to differentiate than products. The function log of L is called the log likelihood. And for our data set, it is equal to the sum of these two terms. Now let's find out for which p this attains its maximum. We differentiate the log likelihood with respect to p and set it equal to 0. Getting rid of fractions, this can be turned into the following equation. And after putting all terms with p on one side, we find p equal to be 3 over 79. At this point, we only know that this is an extremal point of the log likelihood. It might be a local minimum, so we still need to check whether this is a maximum. One way to do this is to determine the second derivative of log of L. This turns out to be strictly negative, and from basic calculus we learned that this means that 3 over 79 is indeed a maximum. So given our data, the maximum likelihood estimate for p is equal to 3 over 79. And so the number of times until you first hit a spoke can be modeled by a geometric distribution with parameter 3 over 79. Now suppose we do not have observations 64, 3 and 12, but a data set small x1 up to small xn, which we model as realizations of independent random variables capital X1 to capital Xn, each having a geometric distribution with parameter p. In that case, the likelihood is given by the following product. Again, it can be simplified by merging all terms with p and merging all terms with 1 minus p. The log likelihood is then equal to the following summation. Now let us continue from here and determine for which p the log likelihood is maximal. After differentiating the log likelihood and setting it equal to 0, one finds that this equation is solved for p equal to n divided by the sum of the observations. Now you may pause the video and check this for yourself. The second derivative is again strictly negative, so that we have a maximum. And we conclude that n over the sum of the capital Xi is the maximum likelihood estimator for p. Note that in this way we have derived a general formula for the maximum likelihood estimator for any dataset generated from a geometric distribution. So this brings us to the following definition of maximum likelihood estimators for discrete distributions. When our dataset is the realization of independent random variables with a discrete distribution, depending on some parameter theta, then the likelihood is defined as the probability of the data. Due to the independence of the capital Xi, this is the product of the marginal probabilities. The subscript theta below capital P is to emphasize that the model distribution depends on a parameter theta. For example, in the geometric example, the role of theta was played by the parameter P. Note that the data, small x1 to small xn, are given to us, and that L is a function of the parameter theta. The maximum likelihood estimate is that value of theta that maximizes the likelihood over all possible values of theta. This value of theta will then be some function of the observations small x1 to small xn. As we argued before, it's often easier to maximize the log of L instead of L itself. Well, this brings us to the end of this video. In the next video, we will explain how this method works for continuous distributions. See you then.